turn the light on. It's kind of like visible. It's sitting there.
0.5 billion U of N. Okay, that's what you're given, okay? And you want to determine the system function representation. So when you're in chapter 5, when they talk about the system function, they're talking about system function is h of z. So you want to determine h of z, which is basically the z transform of the impulse response for the system. And the impulse response you're given is that. And so to determine the system function, of course, you have to rely on either you have to do it the long way and write that out as an infinite sum and all that stuff, or you determine the easy way. You go look at a table on page 87 and find out what the z transform of that function is in terms of n, in terms of z. So it turns out to be, this is just a constant too, so nothing ever happens to constants. They always just sit there. Nothing happens to that. But the z transform, well, let me expand this slightly before I do that. Before you do that. This is the z transform, which sometimes they write like that, h of n, okay? And of course that means go look it up in a table. And so the constant doesn't change. And underneath in the bottom is 1 minus 0.5 z to the minus 1. This is from the table. From the table on page 87. Okay. That page 87 refers to the PDF file that has the text we're using for the MATLAB. Right? So you just go look at that table and you look up the transform. And these two things are transform pairs. And you just have that constant 2 sitting on top. And from looking at this denominator, this thing is written as the same as 2 times z minus 0.5 is, well, let me write it like this. Let me write it like this. 2 times z. Okay. This thing and that thing are the same thing, right? And so the region of convergence, right, is z. In order for this thing, for this thing to be, it has to be 0 is one of the things. And this one has to be greater than z has to be greater than 0.5. The magnitude of z has to be greater than 0.5. In order for that to converge. And if you look at it in this way, you can see that there's a 0 at z equals 0. And there is a pole at 0 equals 0.5. So when you look at it like that, you can draw the pole 0 plot. It's easy to figure out, which is part C. But we're not there yet. Right? This so that was A. So then B. Okay. B says you want the difference equation. The diff equation. The difference equation is gotten from the fact that h of z is y of z divided by x of z. All right. and we said that's 2, and you could use that. It doesn't matter which form you use. It's 2 over 1 minus 0.5 z to the minus 1. Okay. Oh. Okay, and then you cross multiply. You cross multiply and get y of z times 1 minus 0.5 z to the minus 1. That means the delay is equal to 2 times x of z. And now if you go into the, this is in the z domain, right? If you go into the, well, not the time domain, but it's the sample domain, n domain. This turns out to be y of n. That's the inverse of y of z. And this is 0.5 z minus 1 times capital Y of z, that when you inverse transform them, is going to be 0.5 y to the n minus 1. So this multiplication by minus 1 means a delay of minus 1 in the sample. And that's equal to 2 of x of n, because the inverse transform of x of z is just x of n. And then you basically put all the y's on one side and all the, well, you put y of n on one side and everything else on the other to get the difference equation. And so the difference equation turns out to be y sub n is equal to 2x sub n minus, plus, I guess, 0.5 y to the n minus 1 is one way to write it. Okay, and this goes into that. So that, all right, and that's from the discussion of taking the z transforms of time domain expressions. In the past, we went from this type of expression and took the z domain and ended up with this expression and then solved for h of z and got that. Well, now you get this and you just go backwards and find out what the time domain, well, not time, the n domain, which is the index domain, time index n domain is. Okay, and so now see, the pole 0 plot you can read from this expression right here. You have a 0 at 0 and you have a pole at z equals 0.5. Okay? At z equals 0.5. The magnitude of z equals 0.5. So if you use z-plane, you can use z-plane B and A, where B is the coefficients in the numerator of z, and A is the coefficients of z in the denominator. And this will produce a pole 0 plot for you without much trouble. That's a MATLAB command, and it, it generates a pole 0 plot that looks like this. And you end up with a pole, 0 at 0, and you have a pole at 0.5, and that's magnitude at 0.5. There's no phase. The phase angle 0 on that cable. So there's a pole there, okay, and there's a z at z equals 0, and there's a 0 there. Zeros indicate zeros, and X indicate poles. And that's basically the plot. This is the real axis, and this is the imaginary axis, and that's the complex plane. And if you do it in MATLAB, it makes a nice clean plot. If you're sketching it on the board, it ends up sketched like that. So you can tell you have a pole and a 0 and a 0 is at 0 and a pole is at 0.5 because that's, you indicated that value on the plot. That's the pole 0 plot, and then what does it want? It wants the output if the input is x to the n is 1/4 u to the n, okay? So part D is, okay, it wants the output, and I didn't do that, a differential equation, B, C, and this is the pole 0 plot, and this is y of n if x of n equals, what does it equal? One quarter to the n u of n. Right? Yeah. Okay. So, you know that the product of the z transforms, the impulse response, and the input is the same thing as convolving the impulse response with the input in the time domain. In the z domain, it's just multiplication. You can just multiply their z transforms. So the output z transform is the product of the of the h of z, which is the z transform of the impulse response, times the z transform of the input. Well, the h of z we have over there, so that's not a problem. X of z, you got to look that up, and the z transform x of n is equal to 1 over 1 minus 1/4 z to the minus 1, I guess it is. And a fraction is driving up, so we'll put 2, 5 So that's the z transform of the input. So therefore, you have this product, which is this thing here, 2 times 1 minus 0.5 z to the minus 1 times 1 over 0.25 z to the minus 1. You got that. This is a product, okay? So now you have to figure out what that is, okay? So you can either A, use MATLAB, all right? MATLAB and figure it out, or you can just make a guess at it. Because this is a product, you don't want the product, you want to do partial, fraction, expansion. You want a partial fraction expansion of that. So you can either, I think, you can avail yourself of MATLAB to do it, or you can take this thing and multiply it out yourself. That's 1, and you got 0.5 minus 0.75 z to the minus 1, and then you have what's the product? A half of that's plus 0.125 z to the minus 2. That's not too hard to do, right? And then you can use MATLAB or what other techniques. You can also do these partial fraction expansions by evaluating this quantity at I think the roots up here. But basically, you can use MATLAB, and you'll end up with 4 over 1 minus 0.5 z to the minus 1 minus 2 over 1 minus 0.25 z to the minus 1. And you you can see that if you have this fraction and you take 4 of these and 2 of these and add them together, you end up with 2 in the numerator. You'll end up with 2 in the numerator, and if you take the product at the bottom, you end up with the product there. So expanding this into partial fractions isn't so hard because it's real simple. And the region of convergence is the absolute value of z is greater than 0.5. So it's outside that ring. And now remember, this is y of z. That's not what you want exactly. You want y of n. So you have to invert this thing. You invert this thing and get 4, 0.5 to the n times u of n. And this is minus 2 times 0.25 to the n times u of n. And z is the same thing. It's greater than 0.5. Okay. So this thing converts into that thing here. And so that's number 1. All right. And when you do this, MATLAB helps out here. MATLAB plots this thing very easily. And when you get this fraction here, you can formulate the denominator is really easy in the numerator, and then you can use MATLAB here and find the residues. Find the residues and the poles, the residues, the poles, and the constant. Well, there isn't any constant because there isn't any fraction. No, it'll just give you those 2 residues and those 2 poles, and end of story. If you want to avail yourself of MATLAB, otherwise you can just, it doesn't take too much energy to guess. And there's a if you look at the mathematical way, let me think. I'm going to tell you how to do it. If you really want the residues, you can compute them. You can compute them by equals zk. Well, it's harder than it looks. Okay, so this uses the table over here. MATLAB can't help you out with that. You get the table. This is just going in reverse of mathematics. And MATLAB helps you out with the pole 0 plot, and MATLAB can help you out with that. So we'll look at putting that together at the end. All right. Yeah, question.
Will we have access to the table in the test?
Yeah. So now you have a digital filter that's described. So anyhow, so you had the system function is this thing. The differential equation is this thing down here. And this stuff in between is your work, so you're always supposed to show your work. This is a pole 0 plot with things sketched, and so that's C. D, which has this heading up here, y of n if x of n equals that. The answer is that down there. So remember those ideas.